So here's an example. I'm trying to learn conjunctions, right? And I want to know how many examples are sufficient to ensure that with probably at least 1 minus delta, every hypothesis, every conjunction left has at most error epsilon. Okay? Simple application. Here's my expression. To apply this expression to a particular hypothesis space, right? If you think about it, give me a second here. The epsilon and the delta, right, are just things that the user tells you, right? The user, who could be you, says, I want, I want epsilon of 10% and I want delta of 1%, right? And then you're supposed to tell them how many examples they need. The only thing left to figure out is the size of the hypothesis space, okay? Which in most cases is not that complicated. So for example, let's suppose that what I have are conjunctions, right? So Boolean input and I have conjunctions, right? Meaning my concept is just a conjunction of, for example, x1, not x2, x3, okay? So how many of those are there? Anybody tell me? If I have n inputs, how many conjunctions are there over n inputs?
Yeah. 2 to the n.
2 to the n. Anybody agree or disagree? I applaud your bravery in saying something that is different from what's on the slide. That is the kind of attitude we want to discuss. Yeah. So, what is your... I can imagine why you're saying 2 to the n, but why don't you tell me?
Each of the possibilities has 2 options, and there's n options.
What are the options? So I have a conjunction, and you're saying the options are negated or not negated?
Right.
Very good, but remember, for each of the variables, right, I have x1, let's say to x10, right? And for example, let's take the conjunction x3, not x5, x6, right? How many options are there for each variable?
There's a third.
There's a third one, right, which is not included, right? So for each variable, there's not include, negated, and include but not negated. Okay? So for each variable, there's 3 options, so the total is 3 to the n. Okay? So all I need to do is replace size of h by 3 to the n, right? So this becomes n log 3. And, I get, something that most of the time is going to be pretty reasonable. Okay? So for hypothesis spaces that are not too large, packed learning gives you, a nice answer. Okay? Did everybody follow this example? Pretty straightforward, right? Here's another example, our good old friend playing tennis. Okay? Let's say for concreteness that I have 1 attribute with 3 values, which is outlook, 9 attributes with 2 values each, temperature, humidity, wind, etc., right? And my language is conjunctions of features, right? Outlook, etc., or nothing, the null concept. Okay? So what is the size of my hypothesis space in this case? Well, there's the null case, which is 1, right? And then for outlook, what are the possibilities? There's each of its 3 values, right? Plus, what's the other option for outlook?
No.
It's not included in the conjunction, right? So there's 4 for outlook, right? And now for each of the binary attributes, how many possibilities are there? 3, right? True, false, are not included. And there's 9 of them, so I get 3 to the 9. Okay? So my total is 4 times 3 to the 9 plus 1, which is 78,733. Okay? Easy street, right? So here's what my m needs to be. And now let's say that I want to ensure that with probability 95%, right? 95% is 1 minus delta. I want to make sure that my hypothesis has error at most 10%. Okay? How many examples do I need for that? Okay, well, epsilon is 0.1, right? Delta is 0.05. We plug that in, and we get 143. Quite affordable. On the other hand, this is a toy problem, right? On a real problem, things might not be so happy. Okay? Questions? Okay, so we have one unfinished piece of business. Well, actually, let me just say one more thing before we go on, and we will leave Vapnik-Cherepanenko's dimension to next time. The one thing I want to say before we adjourn is packed learning actually adds one more thing to this notion, which is that you have to be able to learn that hypothesis in polynomial time. Polynomial in 1 over epsilon, 1 over delta, and the size of the concept. And this is another important contribution of Valent, is that previous to him, learning theory was irrespective of computational considerations. And statisticians were happy with that, but we as computer scientists can't be, right? If you could approximately correctly learn a concept, but it took you exponential time to do that, this is no use. So pack learning is what we saw before, except that in addition, you have to be able to learn the concept to within delta and epsilon in polynomial time in 1 over delta, 1 over epsilon, and the size of the concept. Okay? All right? So next time we will finish learning theory and we'll talk about support vector machines. And in the meantime, have fun with your last assignment.